Okay, one of the things we're going to be doing in lab is looking at what's called refraction, which is the bending of waves and their changing direction as they come into shallow water near shore. You may know that as waves move toward the shore, they create an orbital motion in the water, and that orbital motion dies out to nothing at a depth that we call the wave base, and that depth is equal to 1/2 of the wavelength of the wave. And so when waves come into water shallower than their wave base, they begin to feel the bottom. That orbital motion brushes against the bottom, and the waves begin to slow down. And that causes the waves to slow down and bend and change direction, which is the essence of refraction. For example, in this animation, you can see the waves in deep water are approaching straight, but they're going to slow down in the shallow water near the headland here, but still go fast in the deep water in the bays on both sides. And that causes the waves to bend and wrap and conform somewhat to the shoreline. That's what refraction is. And one of the things that's interesting about refraction is it's responsible for creating a lot of the famous surfing breaks that we see in Southern California and elsewhere. For example, this is Rincon Point up near Ventura, and the swells are approaching here straight from the Pacific Ocean, but they're slowing down in the shallow water near the point, but still going fast in the deep water out here, and that causes the waves to bend around. So by the time they reach here, you can see the waves changed its direction by about 90 degrees. So that's extreme refraction, and it creates a tremendous right break that's a famous surf spot at Rincon. Here's another example. These two little islands out near Hawaii, the waves are coming in from up here, and they're approaching the islands, and I've drawn the wave crests so you can see them a little bit better. And look at what happens. As these straight waves approach the islands, they slow down and drag in the shallow water near the islands, but they're still going fast in the deep channels away from the islands. And so they change from straight to rather radically bent. That's refraction. One of the things you'll be doing in lab is drawing what are called refraction diagrams, which is your prediction of how waves will bend and change direction as they come into different shapes of coastline. And so it's like you're up in an airplane, and we give you the starting waves here in deep water, and your job is to draw the wave crests showing how you think they're going to bend and refract as they approach the shallow water. You're always going to show them slowing down the closer you are to land where the water's shallower, but going faster where the water's deeper. Probably the easiest rule to remember is the waves tend to conform to the shape of the coastline. Not completely, but they tend to wrap to the shape of the coastline. Well, one of the interesting things about, oh, by the way, this picture here is a pretty good model. See where the land bulges out like this? That looks a lot like Rincon, doesn't it? So you can see it happens in real life right there. Okay, one of the neat things about refraction is that it can cause waves to bend their energy into one spot to make particularly large waves. And a lot of famous surfing waves are created this way. If a wave approaches the land straight, like the hand here, its energy is going to be spread out evenly across the coast. But if refraction causes the wave to bend concave in the direction that it's traveling, like the curved hand here, it's going to cause it to focus its energy into one spot, and that's going to tend to make a really big wave in just one spot. This is shown in this diagram here where you can see an underwater ridge. These contour lines show an underwater ridge, so it's shallower water here and deeper water here and here. And as these swells approach, they're going to slow down over that ridge, but go faster over here. And that's going to tend to focus the energy right over the ridge and create a big wave right there where that X is. And this is the kind of situation we see at a lot of famous surfing spots. For example, this spot, some of you may recognize if you know about surfing waves, is Jaws or Piahi in North Shore of Maui. And a very large wave forms here just in one spot during certain northwest swells. It's a classic what's called an A-frame, where the wave just pops up in the center and is low on both sides. So it's kind of like the letter A. And the reason for that is that the waves wrap to an underwater, oh yeah, here's Laird Hamilton on the Jaws, on the Piahi wave. The waves wrap to an underwater ridge. It's shallow out here in this area, but it's deep over to the sides. And that means the waves start out straight, but they get more and more bent, more and more concave, and that focuses their energy into the spot right over the ridge, giving you both a left and a right break right over that ridge. Well, the wave you're going to be looking at is Mavericks in Northern California, and you're going to be trying to figure out why there's a big surfing wave that forms at one particular spot at Mavericks. Because again, you can see it's a lot like the Piahi wave. It's kind of an A-frame with just the big wave right in one spot. So on a big day at Mavericks, there's a reason why the waves form there, and you're going to figure out why. It has everything to do with refraction.